All right, let's have some fun and work a monster buffer problem. Let's see how long it takes us to do this little six-part problem here. So let's go through it. Here's the question. Our questions. You have a 1 liter solution of 0.1 molar benzoic acid. The Ka is 6.5 times 10 to the minus fifth. Now, what is the formula for benzoic acid? We don't care. All we need to know is it's a monoprotic acid, therefore we're just going to call it HA and leave it at that. Makes it a lot easier. Okay, so part A, we have this benzoic acid. Part B, you're going to add 0.5 liters of 0.090 molar sodium hydroxide to it. Hint, this is going to create a buffer solution. Part C, you're going to add 1 milliliter of HCl, 0.1 molar HCl, to the solution in B. So you're going to make this solution will be made, you're going to add this to it. Part D, you add 100 milliliters of NaOH, 0.1 molar, to the solution in B. Note with Part D, you're going to add this sodium hydroxide to this solution. You're going to kind of pretend you didn't do Part C. Part E, you add 500 milliliters of 0.11 molar sodium hydroxide to the solution in B, pretending C and D didn't happen. Part F, you add 600 milliliters of 0.1 molar sodium hydroxide to the solution in B. So with these right here, when you get to the next one, you pretend the previous didn't happen. When you do F, you're going to pretend C, D, and E didn't happen. You're just going to say, okay, you have B, you add this to it. All right, so the question, what are the pHs of each solution? A through F, we need to calculate 1, 2, 3, 4, 5, 6, 6 pHs using the data we have. All right, so let's get started. We'll start with A. Nice place to start. You have 1 liter of 0.1 molar benzoic acid, Ka 6.5 times 10 minus fifth. What's the pH? Well, we just have benzoic acid. That's in there. That's all that's in there. We've got a Ka, so we need to do an ice table here. It's a weak acid. So we know HA will dissociate into H plus A minus, initial change equilibrium. And our initial concentration of HA is 0.100 molar, and we don't have any of the others yet. Okay, change minus X plus X plus X. 0.100 minus X, X, and X. No problem so far. We know that Ka equals concentration of H plus times concentration of A minus divided by HA. Therefore, our Ka 6.5 times 10 to the minus fifth is going to equal X squared over 0.100 minus X. Can we ignore this minus X? Certainly. And therefore, okay, 6.5 times 10 to the minus fifth equals X squared over 0.100. Tap some numbers in the calculator, and we find X equals 2.5 times 10 to the minus third. And since X equals our concentration of H plus, that's the molarity, equals a concentration of H plus. pH will be the negative log of 2.5 times 10 to the minus third molar. Calculator says pH equals 2.59. Well, that was sweet. That was quick. No problems there. B. Okay, now you're going to add 500 milliliters, 0.5 liters of 0.01 molar sodium hydroxide to it to create a buffer. All right, so let's see. We had this acid, benzoic acid, a weak acid. We're going to add sodium hydroxide, a strong base to it. So our question is, well, what reaction is going to happen? Well, the reaction that's going to happen is our acid, HA, is going to react with our strong base hydroxide. Note this is a weak acid, reacts with a strong base hydroxide. And whenever weak acids react with strong bases, those reactions go 100%. A strong base will react with a strong acid or a weak acid 100%. Not equilibrium here. So this is going to form, okay, H2O plus A minus. The acid base takes the proton, forms water, leaves A minus, okay. And so this is going to be an ICF-like, or an ice-like table. I like to call them ICFs. It's really, at this point, we're actually just doing a stoichiometry problem. We're taking stoichiometry that we learned in Gen Chem 1 and using kind of ice-like tables to figure out the reaction. So I'm going to do initial change final, since it's not an equilibrium, since this reaction goes 100%. I'm going to do it this way. And recall, with these ice-like tables, I like to call them ICF tables, everything needs to be in moles. We need the moles of everything, not the molarity. All right, so we need our moles of HA. How many moles of HA did we have? Well, all of our HA, our acid, came from up here where we had 1 liter of 0.1 molar. So for that, for HA, that is 0.100 moles per liter, 1 molar, times 1.0 liters. We can see that this gives us 0.1 moles. So this is 0.100 moles of HA. No problems. How do we get our moles of hydroxide? Well, we're adding 0.5 liters of 0.09 molar. So for our hydroxide, that is 0.090 mole per liter times 0.50 liters, and we're going to find that equals 0.045 moles of hydroxide. All right, and note at this point, we do not have any A minus. This reaction hasn't happened yet, and we don't worry about the water at all in these tables. And so now, this is not an ice table because we know what our change is. It's not minus X or anything like that. We know this reaction goes 100%. Note we have 0.1 moles of acid, 0.045 moles of base. We know all of the base, the whole 0.45 moles will go away because there's less base than acid. So if all the base goes away, minus 0.045, we have a minus 0.045 here. And we're going to add plus 0.045 moles of A minus. Because all the base, you just have to look at these two, see which one is the limiting reagent, use up all of it, and see how much of the extra reagent you have left over and how much of this product you make. So then it's just math. I'll do the easy math first, 0 there. And then this gives us 0.1 minus 0.045, that is 0.055 moles of HA, all the OH minus is gone, and we have our 0.045 moles of A minus. All right, so at this point you can see we have a HA and we have A minus. We have a buffer solution now because we have HA and A minus in concentrations larger or amounts larger than we would get just through the normal dissociation of HA or the normal base reaction of A minus with water. We have more than that. So this is a buffer solution, and yay, with buffer solutions we can use Henderson-Hasselbalch equation. Recall Henderson-Hasselbalch is pH equals pKa plus the log of A minus, concentration of A minus, the base term, over the concentration of HA. Also recall that we learned from our last time that when dealing with Henderson-Hasselbalch, we can actually leave this in moles since volume will cancel out, our moles per liter will cancel out. Because if we think about it, we'd have to convert this A minus into molarity by dividing by the volume, and this would be divided by the volume, and we take one over the other, it cancels out, so we can leave it in moles, yay. We just have to calculate this pKa. Well, our pKa equals 6.5 times 10 to the negative fifth. Well, that's the Ka. pKa, we have to take the negative log of this. That's the Ka. pKa is negative log of 6.5 times 10 to the negative fifth. And pKa, calculator says, is 4.19. Okay. So our pH equals 4.19 plus the log of the amount of A minus, and we can leave it in moles, 0.45 over 0.055. Hit some numbers on the calculator, and we find that the pH is 4.10. And that'll be the pH for solution B when you took solution A, our benzoic acid, and then you added some sodium hydroxide to it to create that buffer. All right. Question C. You now add 100 milliliters of HCl, 0.1 molar HCl, to this buffer solution. So here's our buffer solution that we have right here. B calculated our buffer solution, our pH, and the amounts of acid and conjugate base. And so now we are going to add acid to it. 100 milliliters of 0.1 molar HCl. Okay, so, don't have much left on this page. I'll have to turn the page. I'm going to have to be flipping back and forth every now and then just to make sure I'm keeping track of what's going on. Okay, part C. All right, let's see. Let me remind myself we're going to add 100 milliliters of 0.100 molar HCl to our buffer solution from part B. Well, let's think. What all did we have then? If we had 100 milliliters of HCl in there, what reactions take place? Well, recall that with our buffer solution, we have some of HA, we have some of A minus. So that means we're going to have HA, and we're going to have A minus, and we're going to have HCl, because we're going to throw in this hydrochloric acid. And so what reactions will happen? Well, do acids react with acids? Not really. So HA and HCl won't react with each other, but the conjugate base, A minus, will react with the HCl. So we need to do an ice-like table, or an ICF table, to figure out what's going to happen when A minus reacts with HCl. So, well, let's just write down A minus plus, note, I'm not worried about the chlorine, it's the H plus of the HCl that's the main deal here. And note, this is a weak base. Conjugate base of a weak acid is a weak base, but HCl is a strong acid. Weak base, strong acid reactions go 100%. And this will form HA. All right. Initial change, final, since this is a 100% reaction, this is not equilibrium, I put my final there. Well, recall that these tables need everything in moles. So I need to figure out the moles of each. Well, I'm adding my HCl to my buffer solution. Good news, in part B of this, we calculated my buffer had 0.055 moles, 0.055 moles of HA, 0.045 moles of A minus. So let's just plug that in right here. 0.055 moles of HA, 0.045 moles of A minus. The question is, how much H plus, how many moles of H plus are we adding to this A minus? Well, amount of H plus moles is going to be 0.100 molar times 0.100 liters equals 0.010 moles of H plus. Plug it in, 0.010 moles of H plus. All right, which is the limiting reagent? Well, it's 1 to 1 to 1, limiting reagent. H plus is a limiting reagent. So we know all of this H plus is going to get used. It'll all get converted into HA, and we have to take off 0.010 moles of A minus, which gives us 0.035 moles of A minus, no H plus left over, 0.065 moles of HA. Let's evaluate. Where are we now? We have A minus, we have HA, we have a buffer solution, we have Henderson-Hasselbalch. pH equals 4.19, our pKa from before, plus a log of A minus 0.035 divided by HA 0.065. And a little calculation on our calculator, negative log, blah, blah, blah. And we find the pH is 3.92. Lovely. Okay, we're cooking. We're halfway through. How much harder can it get? Okay, let's keep going. D, what did we have for D? Well, if you recall, D says we were going to add 100 milliliters of 0.100 molar sodium hydroxide, NaOH, to our buffer solution in B. So we're going to pretend this didn't happen. We just need to add this to our original buffer solution in part B. And okay, well, recall from part B, we had HA and A minus. That was our buffer solution, HA, the acid, benzoic acid, and its conjugate base. And then we're going to throw in hydroxide. Well, what's the hydroxide going to react with? Do bases react with conjugate bases? No, bases are going to react with acid. If you got a conjugate base, an acid, and you throw in strong base will react with the acid. So our equation, our reaction that will happen is HA, our acid, will react with hydroxide, the base, and will form H2O plus A minus. Note, as we said before, this is a weak acid, this is a strong base, and weak acid, strong base reactions go 100%. So this is not equilibrium, so therefore we need the ICF here. We need this table. And okay, we need our initial values. Well, we're adding it to B, the solution in B, and luckily our initial values for B were the same for A minus and HA up here, except HA was 0.055, A minus was 0.045. Water, it's never going to show up in an equilibrium or any of these calculations, so we don't worry about it. So then we need the moles of OH minus. Hopefully we can see, okay, we have 0.100 molar OH minus. And we have 100 milliliters, which is 0.100 liters. And our OH minus moles is 0.010. All right, which is our limiting reagent, 0.05, 0.01. So we know we're going to lose all of this 0.01 molar OH minus. It's going to react with 0.01 molar HA. It's going to create 0.01 moles, excuse me, moles here, not molar, but moles of each. 0.01 moles of A minus. So this gives 0 OH minus left over. 0.045 moles of HA left over, and 0.055 moles of A minus produced here. We have HA, we have A minus, we have a buffer solution, Henderson-Hasselbalch, pH equals 4.19 plus the log of the base, 0.055, over the acid, 0.045. pH equals, tap, tap, tap on the calculator, pH equals 4.28. Okay, so at this point, let's look what happened. We had our buffer solution. First, we didn't have any buffer, and the pH was 2.59. We added base to make the buffer, and the pH went to 4.1. Since this is a buffer solution, when we add acids and bases, we expect the pH to not change that much from 4.1. So note in this, when we added acid, it made it a little more acidic, but it went from 4.1 to 3.92, a difference of 0.2 pH units. That's not too much for adding 100 milliliters of 0.1 molar acid. Then we added 100 milliliters 0.1 molar base, and the pH went from 4.1 to 4.28. So you can see, adding some acid, adding some base to these buffered solutions, and the pH does not change very much. All right, okay. The next step, E. Well, let's remind ourselves what we're doing for part E. Well, for part E, we're going to add 500 milliliters of 0.110 molar sodium hydroxide to B, to our original buffer solution. Okay, so we're adding sodium hydroxide again, so we know it's going to be HA, A minus, and OH minus. We know the OH minus is going to react with the HA. So far we're looking pretty good. We know that our reaction is going to be the HA plus the OH minus will react 100% to water and A minus. Initial change final because it's a 100% reaction of weak acid, strong base. And our initial, remember this is our initial buffer again, our initial buffer B, so HA is 0.055 moles, A minus is 0.045 moles. We're not going to care about the water, so we just need to find the number of moles of hydroxide. Okay, number of moles of hydroxide. That would be, what would that be? Okay, that's 0.110 molar times 500 milliliters, 0.500 liters, and so that equals, oh, check that out, 0.055 moles of hydroxide. Oh, 0.55 moles of hydroxide, we have 0.55 moles of acid. You're going to subtract 0.55, same number. That has no HA, no OH minus. We have to add 0.055 because this is the product. And that gives us 0.100. And note that is moles of A minus. Okay, let's look now. What do we have in solution? What do we have in here? We have A minus. We have water. And that's all we have is A minus and water. Note, we don't have any HA at this point. We just have A minus and water, which means this is no longer a buffer solution, which means we can't use Henderson-Hasselbalch anymore. So the question is, how do we get the pH of the solution when all we have is this conjugate base? Well, recall that HA is a weak acid, so we have the conjugate base of a weak acid in water, and the conjugate base of a weak acid is a weak base. So we've got a weak base in water. We need to look at the reaction of that weak base, A minus, plus H2O, in equilibrium, since it's a weak base, no strong anything, in equilibrium with HA plus OH minus. Since this is equilibrium, we're back to ice tables. Initial change equilibrium. And now we need the initial concentration of A minus. Oh, well, we don't have that. This is the moles. For ice tables have to be in molarity. We need the molarity here for our ice tables. So, okay. We've got A minus. How do we figure out the molarity of our A minus here? Well, if we have 0.100 moles of A minus, well, molarity is moles per liter. What's our volume? Well, we added 500 milliliters of our NaOH. What was our original volume of solution? Oh, when we look way, way back for B, realize that we have 1.5, whoa, here we are, 1.5 liters. So we have 1.5 liters here. So that's 0.00 moles divided by, well, 1.5 liters plus our 500 divided by 2.00 liters. Okay. And so then the concentration is 0.050 molar. So concentration of A minus here is 0.050 molars. We're not going to worry about the water. And this is before any dissociation. So we have minus x plus x plus x, 0.050 minus x, x, and x. Okay. Now recall that this is the base reaction. This is A minus in equilibrium with H2O, going to HNOH. This is the A minus, so the equilibrium constant for this is the Kb. Kb is going to be the concentration of HA divided by the concentration of OH minus divided by concentration of A minus here. But do we have a Kb? Were we given Kb? No, we were not given Kb. But since this is the conjugate base of our benzoic acid and we had the Ka of benzoic acid, we recall that Ka times Kb equals Kw. Plugging in numbers and rearranging, Kb is going to be equal to 1.0 times 10 to the minus 14th divided by, what was that number? That was 6.5 times 10 to the minus 5th. So our Kb is going to equal 1.5 times 10 to the minus 10. Okay. So plugging all that in now, we've got 1.5 times 10 to the minus 10 Kb will equal x squared over 0.050 minus x. Can we take the shortcut? Yes, we can. So we can ignore that minus x, which means 1.5 times 10 negative 10th times 0.050, and square root that. We have, what do we have? I'm going to bring it all over here. X equals 2.7 times 10 to the minus 6. Now, X is our concentration of hydroxides. Let's put molarity on there. That's our concentration of hydroxide. I need the pH. For me, it's easier at this point to take the negative log of this number since it's in my calculator. And so I take the negative log of 2.7 times 10 to the minus 6, and that's my pOH. Negative log of 2.7 times 10 to the minus 6. The pOH equals 5.56, and therefore pH, remember, pOH plus pH equals 14, so you subtract 5.56 from 14, and you get pH equals 8.44. Okay. Well, let's take stock. That was a long step there. Here's the deal. This tells me your worth as a chemist almost. If you can get to this point and get this part right, because think about all that you have to know in order to get part E right. Man, there is just all sorts of moles, molarities, what reaction is happening, Ka versus Kb, POH. We have essentially summed up the entire acid base chapter, the previous chapter, in one part of this problem. This is awesome. You gotta love this. Hint, you better learn to love it, or else this is going to be one of your nightmares. All right, but good news, we're not even done yet. We have part F to go. But before we go to part F, something that I want to point out to you is that we were adding base, add a little bit of base, add a little bit of base, the pH doesn't go up, but once you add just enough base such that you've canceled it out, note that canceled out the acid, note that the pH rose from 4 to 8. Huge pH change when you got rid of the buffer solution. All right, the last step, part F. With part F, what are we doing with part F? In part F, we are going to add, we're going to add 600 milliliters of 0.100 molar NaOH to our solution in B. All right. So, what's going to happen? Well, recall from before with our solution in B, we've got HA and A minus, and now we're adding more OH minus. We know our OH minus, what we're going to have is going to react with the HA. So just like we did in the last one, HA plus our OH minus, 100% reaction, weak acid, strong base, goes to water plus A minus. Since 100% reaction, we do ICF, initial change final. Since this is our original buffer solution in B, recall we have the 0.055 moles right here. We've got our 0.045 moles of A minus. We're not going to worry about the water. We need to find out the number of moles of OH minus. Just as we've done before, we've got 0.100 moles per liter times the liter, 0.600 liters. Math is easy. That gives us 0.060 moles of A minus. 0.060 moles of A minus. Okay. Which is our limiting reagent now? Oh, we've got more OH minus than HA. So HA is the limiting reagent. This will come down to 0 because we can only subtract as much, we can only react as much OH minus as we have HA. So we're going to get all that HA gone, minus 0.055 here, plus 0.055 here. So that gives us 0.005 moles of OH minus left, 0.100 moles of A minus when we finish up this table. Okay. When we finish up these tables, these ice-like tables or these ICF type tables, we always say, well, what do we have in solution? What do we have now? Well, we have A minus. Recall A minus is a weak base. We have OH minus left over. OH minus is a strong base. So we have a solution of strong base and weak base. Remind me, when you have a solution of strong base and weak base, what determines the pH of that solution? That's right, only the strong base. It's only the strong base that determines the pH of this solution. In fact, having that extra OH minus in there means that this A minus is not going to want to react with water to form more OH minus. We already have a lot of OH minus in there. Le Chatelier tells us that A minus will not react that much with water. When you have strong base and a weak base, the pH comes from the strong base, which is nice. So we've got the strong base here, but note this is 0.005 moles of strong base. We need the concentration of strong base. because pH will equal the negative log of the concentration, which I'm just going to write it all right out here, 0.005 moles divided by, okay, what's our final volume? Well, recall we had the 1.5 liters from B. Man, that was 2 pages ago. From B, we had 1 liter. We had 0.5 liters of this solution to give us B, so that's 1.5 liters. And then we added 600 milliliters, so that is 2.10 liters. Oh, let's do some math. 0.005 divided by 2.1. Take the log of that, make it negative. Oh, but wait a minute. This is OH minus. This isn't pH. This is POH. Watch out for that mistake. Very common mistake. Even professors will make it sometimes, or perhaps they did it on purpose to show that you'd better watch out for your mistakes. Maybe that's the case. Yeah, I did that on purpose. Okay, so that's the POH equals 2.62, and then we subtract it from 14. The pH equals 11.38. Okay. Something I want to know about this last little bit. When we looked at part E, we had 0.055 moles of OH minus, and the pH turned out to be 8.44. When we go to part F, we go to 0.06. So we're only adding 0.005 moles of OH minus more than we did before. But the pH jumped from 8.6 something? 8.44. Add that little extra bit of strong base, and it jumps from 8.44 to 11.38. Why did it jump so far? How come it jumped so much with adding just a little bit of base when in our previous problems we were adding 0.01 moles of base? We were adding a lot more base and the pH hardly changed at all? Because these are buffer solutions. Here is a prime example here how adding base to a buffered solution does not change the pH very much. Adding just a little bit more base, 0.05 moles, a little bit more base to a non-buffered solution greatly changes the pH. All right, and so now we're done with this nice little 6-part buffer problem. Only took us a little over 35 minutes to do it, and that's when we knew what we were doing. You need to practice these problems because I can guarantee you it's going to take you an hour or 2 hours or so to get this down. Go through this problem. Make sure you're very good at these problems. You need to get this problem down to under half an hour. Truthfully, you need to get this problem down to 15 minutes or less if you can. Good luck with that.